Okay. Hi, Abhishek. Welcome to this mock interview round for PyTorch interview questions for Generative AI Engineer at TCS. So here we are going to ask certain questions where you have to explain us how you use PyTorch to design, train, troubleshoot, optimize, and deploy generative AI models for NLP and image generation use cases in an enterprise setting with verification, MLOps, and production constraints. And the first question is, how have you used PyTorch in a generative AI project, and why did you choose it over other frameworks for that use case? So
Okay,
let's know the
so
use case. Let us know
hmm,
how you used it and why you
mhm,
have opted it with respect to other frameworks like TensorFlow and so.
mhm. Okay, so when it comes to the real project context, in one of my Gen AI initiative, I used the PyTorch to build a domain-specific conversational assistant by fine-tuning an open source LLM model. It was open source Llama model on some proprietary domain-specific textual data. So the project required domain adaptation, and so which was done through uh, fine tuning like PEFT or LoRa and some custom reward modeling for the alignment. So this PyTorch module served as a bedrock for the custom data loading pipeline, uh, training the loop orchestration or precision scaling. So when it comes to the trade-off, like why PyTorch, why not other thing? So I I chose PyTorch over other alternative like TensorFlow due to specific architectural and ecosystem advantage crucial to LLM engineering. So first we can say it's a native ecosystem integration. So like integration with Hugging Face or Deep Speed. So modern Gen AI development rely heavily on HF Hugging Face ecosystem, the transformer, accelerate, PFT. So these libraries are uh, natively written in PyTorch. So choosing PyTorch allowed me to kind of seamlessly load the model architecture and apply the LoRa adapter on top of them. Second, we can say the debugging is so standard Python debugger uh, work directly with the PyTorch client because it is written in Python only. So when debugging a complex custom loss function, it could be mass cross entropy for token prediction or some some other loss function. I could inspect the gradient weight and tensor shape just interactively at the runtime. And yeah, this one, and also the PyTorch have this DPP, that data parallel distribution thing. So yeah, this was also one of the reasons. So I mean, if it is scaled and some GPUs, enterprise GPUs are involved, then these parallel processing of PyTorch property is really helpful. When it comes to the productivity and the outcome, so obviously it provide a reduced developmental latency because PyTorch have automatic precision involved to train the model and to reduce the memory footprint. The training speed optimization is also really good. So the overall we could simply use a distributed acceleration backend so to speed up the overall training time. And uh, there is a another advantage of seamless production deployment. So because PyTorch offer a clean pathway to compile the model from torch.compile, we can it could be used for transitioning the fine-tune uh, weights into the highly efficient low latency interface engine like VLLM, Vision LLM, or any of the interface server. So overall, it provide a zero structural, I mean, zero project structure refactoring. It can be used as Go. Yeah, so this was my answer for that.
Okay, great. The next question is, Can you walk through the structure of a PyTorch training pipeline for a generative model from data loading to checkpointing?
Okay. So first, so the initial phase would be, the initialization. So we set the seed across Python, NumPy, PyTorch to ensure a deterministic behavior because it need to be tracked at later stage. So, it initialized the experiment tracking weight and bias. Then for data pipeline, uh, it uh, mm, we inherit some utility function from Torch utility library to handle the text preprocessing and tokenization, and further wrapping this inside data loader to manage the batching, shuffling, and also multi-processing on go. Then there is a infra aspect also. So we could initialize the model class and move it to the target device. Target device, when I say, I'm referring to CUDA or something similar to this. And we can create an instance of the optimizer, whatever optimizer we are using, Adam or something like that.
Hmm.
And
Adam or BC.
uh, hmm. And then yeah, the training loop, we can handle the forward and backward step. So mm, we can run a forward to pass the compute prediction, and using this we can calculate loss, automatic entropy loss on the go. We can call the optimizer to clear the previous gradient, and we can run backward using using that loss backward property to compute the gradient, and then we can execute optimization and schedule a step on that to update the model weight. At last, for checkpointing, log batch metrics. It can be used for the log batch metric to track the overall framework. At the end of each iteration or each epoch, uh, it save a comprehensive checkpoint using torch.save. So it have the model state and the optimizer state, everything in that. So overall, it the checkpointing, it provides us a log of overall model and what happened overall training iteration. Yeah, that's.
Okay, great. So the next question is, in PyTorch, how do you implement and train a variational autoencoder for image generation? And what are the key loss components?
Mhm. Okay, so when we talk about the architecture revolving around VAE, so VAE is split into two subnetwork. Uh, you know, uh, we could say one is the encoder, other is the reparameterization. So the encoder, it compress the input into some continuous values, continuous latent space. So instead of mapping directly to a fixed latent vector, it output two distinct vector, the mean and the log variance. So in backend it generate some kind of statistical distribution for the analysis using these two values. For in reparameterization, the uh, it is used to train the network end to end by using the back propagation technique. So we cannot sample directly from this latent distribution which is generated because it's not differentiable. The function is not differentiable. So instead, we use this back propagation technique. And what is the other factor key? And during the yeah, there is also use of KL divergence here. So mm, for in loss during the loss calculation and loss reconstruction. So it kind of scale divergence compare the actual the empirical values to the actual values of the statistical distribution. So you can do the tracking, and there is a uh, monitoring monitoring aspect also. So during training, uh, I monitor the loss terms separately rather than combine to catch the imbalance easily. So I mean, it was done through a lot to track the structural quality over time. And I don't know, I did a periodic evaluation by generating the samples from that fixed random grid and tracking the latent space.
Hmm.
Mm, yeah.
Okay. Any ideas on what is posterior collapse or latent dimension choice?
Yeah, I do remember these things. I mean, it is related. This posterior collapse is related to that KL divergence thing only, but I'm not able to recall these things. Uh, so I mean, latent dimension, it is used uh, for some reconstruction purpose. However, I need to revise these two things. But what I remember is I'm
Great.
telling you.
No problem. You can just touch these points also, posterior while
Mm,
preparing.
mm,
So have a quick
mm.
understanding about these. Now, let's get to the next question. So the next one is how would you build a GAN in PyTorch and what steps would you take if training becomes unstable?
Okay. If it become unstable,
Mhm.
well, the GAN also, it has two parts. It stands for generative adversarial network. So there is one generator, one discriminator. So the generator take the random noise and and project it to some target data set, like create some, let's say, creating some generating some synthetic image, uh, and and discriminator, it act as a binary classifier. So that take an image, either real from dataset or fake from generator, and output the probability score, predicting whether it is real or synthetic. So yeah, through some so sigmoid activation function and some convolutional neural network thing. So what would you take if training okay okay if it become unstable, then
So you can come to these stabilization techniques in case if you can recall label smoothing, gradient penalty, Wasserstein loss, spectral normalization, architecture tuning. Otherwise, we can skip to the next one. You can touch these in your preparation.
yeah, yeah,
Okay, so
it need to
you
be.
have to you have to touch stabilization techniques. Okay,
Yeah,
that would
yeah,
be
sure.
more important as well. Now, coming back to the next point, what are the most important PyTorch debugging techniques you use when a model trains but does not improve? So you're constantly training the model, but it is not getting improved.
Okay.
So how would you debug those? What are the debugging techniques in PyTorch?
Okay, so suppose if a model is running smoothly but the loss are flatlined, so definitely there could be some semantic bug rather than syntax or memory failure. Uh, for this, I would try to isolate the issue systematically, slicing the debugging workflow in few stages from input to the end. So first, I would check the data pipeline itself, from where data is coming in.
Mm.
So before changing any architectural weight, so I would ensure that model is actually receiving what it intend to process. First thing, because if it is a flat line, failure could be at the data pipeline level itself.
Mm.
So first, batch inspection. I would be doing the batch inspection. Manually, I would be intercepting the training batch from the data loader, and then decode the token ID back into text and or reconstruct that into some kind of a visible asset. So this would ensure that data is not corrupted during dynamic slicing. Then another issue could be at the data pipeline level is the label misalignment.
Mm.
So I would audit the target tensor to confirm the token or the target indices matches the input distribution. And also I would ensure inputs are complete uh, you know uh, aren't saturating due to uh, missing of some transformation at the data pipeline level. Then if the data pipeline is intact, then I would try to check the training loops
Mm.
and do some sanity check there. So I would verify if the optimizers are in place, like zero gradient and all these things. If it is an explicit, if it is at the beginning of every training batch iteration or not. So if it is not there, then this will cause the gradient to accumulate infinitely across the batches. So it would result in some noise creation. Then I would even uh, check if the model train is active or not during the gradient loop, and if evaluation is enforced or not during the gradient loop.
Okay.
Then at the device level, device, I mean, CUDA and all these things. So there some CPU fallback issue, need to be checked if that is happening or not.
Okay. So, can you also explain what does this overfit a small data set means to ensure that the system can learn?
So suppose if a batch is small, if let's say if I isolate a subset of data, let's say one or two sample, and attempt to overfit it entirely over, let's say, 50 iteration. So the diagnostic would be if the model cannot drive the training loss
Mm.
to almost zero in single batch, then your architecture is not working. Something is completely missing or it's broken.